Okay, let me restart. Welcome, everyone. Today we have the pleasure to have Dr. Wang from University of Idaho, Department of Computer Science, as a guest speaker to talk about some recent research and actually a platform built by her on semantic segmentation of remote sensing images. This is a very new method and technology recently developed by the remote sensing community. And I think there's relevance to this community because in this committee, we talk about semantic technologies and also the applications. And besides the semantic tech committee in ESIP, we actually have a few other working groups, semantic harmonization, schema.org, the one Ruth just mentioned, and also people working on the suite ontology and also soil vocabulary and soil ontology. Maybe I will also miss a few other activities. We do have a lot of people interested in semantic technologies and applications. So with that said, I may give the floor to Dr. Wang to give her presentation.
So let me share my screen first. Oh, can everyone see my screen?
Yes.
Okay.
Yeah.
Okay, so good, good afternoon, oh, sorry. What I did, okay. Good afternoon, everyone. My name is Wang. I'm currently a postdoc fellow at University of Idaho in the Department of Computer Science. I got my PhD in geography, and my study focuses include remote sensing, GIS, and deep learning. I'm very glad to give a talk to the ESIP Semantic Technology Committee today. I have been studying the semantic segmentation remote sensing for several years. Today, my topic is advancing remote sensing, benchmark insights, and a powerful interactive segmentation tool. Now, let me start my presentation today. So, semantics in the domain of remote sensing involves understanding and extracting meaningful information from remotely sensed data. Semantic analysis is usually used to characterize or classify the data into identifiable specifics like type of vegetation, land use, water bodies, urban areas, or anomalies like oil spills or forest fires. This is usually done using machine learning or deep learning techniques. A clear understanding of semantics can help differentiate between various types of landscapes and objects. And in recent times, semantic segmentation is one specific approach that is extensively used in remote sensing. It is a pixel-wise labeling approach, and it helps in understanding the context of the entire scene rather than identifying individual objects. Semantic segmentation, in the context of remote sensing, is a method used to classify each pixel in the image with a corresponding class label. In other words, for every pixel in a satellite or an aerial image, semantic segmentation assigns a class label delineating every object of interest in a scene with its exact shape and location. But what happens if you want to detect a different object that isn't present in the predefined set of classes? This is where interactive segmentation comes into the picture. Interactive segmentation has the ability to classify any object. The aim is to find out classes in a data sample along with providing a clear distinction between the classes' precise locations. Each annotated pixel in the digital image will belong to a single class, where the output is a mask that outlines the shape of the object in image. But how would the machine be able to classify it? You will need some user input. For example, the user could just say a right object's name and the model would correctly classify the pixels in image. There are some simpler interactions. First, the points. In this method, the user can place points in an image to identify the desired object, Each time the user places a point, he sees the mask as the output. Then if he sees misclassified regions, he places negative points to indicate that the model made wrong predictions. And the final mask is a result of these interactions. And the second one is the bounding box. The user can draw a bounding box around the object he desires to classify, and the model uses this information to classify the red pixels. And the last one is the scribbles. The user can draw a rough skeleton of the object with a free-form draw tool, and then the model uses this as input for predicting the mask. And in my study, I focus on the point-based, just the first one. So later you will see more figures like the first sheep. In recent years, many advanced interactive segmentation approaches appeared in computer vision field, like simple click, focal click, and the segment anything, the SAM model. That SAM model, just for example, was proposed by the Meta AI in this April, which is popularly discussed in recent months. And here is an example result from their paper. You can see this is original and a photo took from the supermarket, but all vegetables and all fruits were segmented out. SAM is able to automatically segment out objects based on giving a word or providing the points. And in remote sensing, the concept of interactive traditionally refers to the process in which the researcher or analyst plays an active role in interpreting and classifying remote sensing imagery. Before the advent of AI or machine learning, interaction was more direct and manual, but it was an indispensable part of the process. Deep learning-based interactive segmentation methods can handle challenging cases, such as urban satellite images with complex features, occlusions, and variable lighting conditions, which are commonly encountered in remote sensing applications. But the use of the deep learning for interactive segmentation in lab cover classification is less explored. Therefore, in my study, I conducted a benchmark study to evaluate how those most advanced interactive segmentation methods perform in remote sensing images, and also developed an interactive segmentation tool, especially for the remote sensing images. Therefore, in my study, there are three main objectives. First, I investigated how well the current state-of-the-art interactive segmentation methods perform on two remote sensing datasets. And second, I evaluated an interactive segmentation methods on diverse land cover types, object sizes, and different bond combinations in remote sensing. And finally, cooperated with my colleagues, we developed a novel online tool for interactive segmentation using the remote sensing images based on the findings from the experiments in this paper, and also further compare our tool with the popular SAM model. And first, let me talk about the dataset I used in my study. I used the dataset published by the International Society for Photogrammetry and Remote Sensing, the Potsdam dataset and the Wang dataset. The Potsdam dataset has a spatial resolution of 5 centimeters, and the Wang dataset has a spatial resolution of 9 centimeters. The Potsdam dataset contained the 4 bands, the red, green, blue, and near infrared. And the Wang only contains 3, red, green, and near infrared. And the dataset both include 5 classes: the buildings, trees, roads, low vegetation, and cars. And these 2 datasets were really popular in the deep learning semantic segmentation researches, which is to evaluate how they can apply to the remote sensing applications. And just like I said, in my first part of my study, I conducted a benchmark. So I conducted benchmark studies. So I need to firstly to introduce the representable models. The first one is the reviving iterative training with mask guidance for interactive segmentation, the RITM. And the second one is the cascade forward refinement with the iterative click loss. And the third one is focal click and the simple click. And the last one is segment anything model, the SAM. I won't talk too much about how their architecture looks like. And these 5 just the most recent and all published in the top journals and top meetings in recent 2 years. But what I need to talk a little bit more is the cascade forward refinement approach developed by the second author. The cascade forward refinement approach, the CFR, introduces an innovative inference strategy for interactive segmentation that allows for iterative refinement of the segmentation results without the need for multiple needs. And this methodology enhances the user experience by reducing the effort required for refining the segment and ultimately improves the quality of the final segmentation results. And based on the findings from this paper, I found it's a really good approach that can use to improve the other ones. So in my study, I further improved the RITM and the simple click models using the CFR method. So just remember, finally, I have 8 models that should be evaluated in my paper. I know there's a lot of introduction about this complicated. Just remember, finally, I evaluated 8 models in my paper. And then I want to say, in my evaluations, there are 2 steps. The first step is I evaluate models with the initial weights, with just keep out hyperparameters the same as how author published them. And then I selected the better models for fine-tuning. Fine-tuning is a method in transfer learning. In fine-tuning, we often keep the early layers weights fixed because they carry the generated features like age detections, texture recognition, and then we fine-tune one or several of the last layers which carry more task-specific features. So in this study, we use the partial remote sensing datasets for fine-tuning to make the models better for classifying the remote sensing images. And I evaluated the model performance using the number of clicks and the average click number required to reach the target intersection over union. Intersection over union is a popular evaluation metric in the semantic segmentation tasks. So the number of clicks, the NOC, is a measure of how many clicks or interactions a user provides to achieve a desired result. Lower NOC suggests a more efficient model as it requires fewer user interactions for accurate segmentation. So in my study, I reported the NOC to achieve the IOU at 4 levels, to reach the 80%, 85%, 90%, and 95%, which correspond to the metrics NOC 80, NOC 85, NOC 90, and NOC 95 respectively. And here I show the first table, the evaluation result for all 8 models with the initial weights. So here we can see that the simple click CFR model performs the best at a higher IOU levels. It demonstrates that its ability to achieve finer and more accurate segmentation results. And it is important to know that as the desired IOU level increases, the efficiency of all models declines significantly, while the least performing models at an 80% IOU level requires less than 7 clicks, but at the 95% IOU level requires approximately 14 clicks. This trade-off between the precision and efficiency becomes evident at higher IOU thresholds. And we can see that the focal clip and the SAM, they didn't perform that good compared to other models. So in the further fine-tuning evaluation, I didn't include these 2 models. And here is the second result, shows the model results after fine-tuning. We can see here the simple click and simple click CFR models consistently exhibit the superior performance with lower click counts across all IOU levels. And here is another figure. This figure illustrates a comparative analysis showing the fine-tuned models consistently outperform non-fine-tuned models based on the mean IOU values. We can see here this part is the trains from the fine-tuned models, and this part is the trains from the non-fine-tuned models. As the click count progressively increases, the fine-tuned models consistently outperform their non-fine-tuned counterparts. However, the performance gap, as quantified by the mean IOU values between the two types of models, steadily narrows by the point where the click count is 10. The superior performance of the fine-tuned models, though still discernible, largely approximates that of the non-fine-tuned models, with scores predominantly hovering around 0.9. And further, we know that in the urban classification, we not only consider the overall accuracy, we also think more about how they perform differently at different land cover types. So this table shows the performance variations in different classes for interactive segmentation models. And here we can see that the building class optimally segmented with fewer clicks, indicating the model's effective segments with less user.
Hi, Jeff.
Oh, sorry.
Seems your link was frozen for about 10 seconds. Yeah, can you just maybe restart on this slide? The experiment and result. Yeah, this one.
What do you mean link frozen?
It's just like your link was lost for about 10 seconds.
Oh, did I? You didn't see my presentation?
No, just 10 seconds. Don't worry.
Oh,
so
okay.
Can you just restart on this slide?
Restart on this slide. Okay.
Yeah. Thank you.
Oh, let me talk over about this slide. So like what I said, in urban classification, we not only consider the overall accuracy, but we also consider like how different land cover, how the models or classification methods perform on different classes. So here is the table that shows the performance variations in different classes for all these different interactive segmentation models. So here we can see that the building class optimally segmented with fewer clicks, indicating we can see that the model effectively segmented with the less user input, but the low vegetation class needed more clicks, signifying a higher challenge. So here I provided two examples of the building segment and the vegetation segment. And for the first one, you can see for the building segment, if I want a segment out of building, I need 3 positive clicks and 2 negative clicks. But for the vegetations, it needs much more. And from these two examples, it might be easier to see that might be because the building has a more regular shape, but the shape of the vegetation, the low vegetation like the grassland, it is more irregular and more unique, which is hard for the model to tell. And moreover, in remote sensing land cover classification, the size of the surface objects is also a crucial factor. I also conducted a further investigation into the relationship between the size of the surface objects and the number of clicks required to achieve various IOU threshold. So here is the table, shows the result. Here I only show the building result as an example. So this table, the segment size of the building class was divided into 5 categories using the quantile method. And here I also provide some example patches to see how the different size of building looks like. And so it is notable that the larger building segments require fewer clicks to achieve the satisfactory IU levels across all the models. And it indicates that the segmentation algorithms are more efficient in dealing with the larger building segments than smaller ones. And just call back from the result from the previous slides. When comparing the building class performance with other land cover classes, we also observe that buildings generally require fewer clicks for successful segmentation. And this again attribute to their regular and well-defined shape characteristics, which facilitate the interactive segmentation process, resulting in reduced click requirements for different segment sizes. And then, just like what I said in my third objectives, we further compare our model to the SAM, because we know that the SAM was really popular in recent months, and it is powerful and it is supported by a really huge data sets. But why it didn't perform well on the remote sensing data set? So we have compared the SAM, and the best model pointed out in this paper, the simple click. So here is a figure compares the segmentation results of simple click and SAM by point result. So simple click segments a whole building with one click, where the SAM for one click in the same location, SAM only does half. Require additional clicks for full outline and protecting jagged, and also we can see it produces the jagged edges. And the simple click achieves satisfactory results with just 1, 2, 3 clicks. But the SAM requires more points and displays a continual roughness in the edges. And also in the SAM paper, we also compared SAM with the RITM, focal click, and the simple click as well. Consistent with the conclusion from the figure I show here, SAM can achieve lower single point performance. It indicates that when the number of click is limited, especially in the range of 1 to 5 or 1 to 3, SAM can more readily yield a relatively positive results with an IOU exceeding 70%. However, for more refined segments requirements, simple click or simple click CFR can more easily help the IOU to attain over 90% with more input, given the diverse shapes or landmark objects in urban land classification. So also the speaker also hints that the SAM might not excel in outlining the edges of the landmark objects. This could be the reason why the classification results of simple click or simple click CF models are superior. So based on all the findings from this study, here is the demo video. I developed a tool called the RSISEG. Here is a demo video of the developed on-time tool. So drawing on the findings from the above experiments, we developed the tool for interactive segmentation, especially for the remote sensing imagery. This tool seamlessly integrates models that have been fine-tuned with the remote sensing data derived from our early experiments, in addition to incorporating to the original SAM model, since many researchers would like to compare these models to the SAM. And to optimize its functionality for remote sensing data, the tool is engineered to efficiently process the TIFF files and export the result in GeoJSON format so that you can re-editing your results in those GIS software platforms. And so in today's demo, I just show some really important functions, but important functions, we still have many small things that are really interesting. So here is a figure, just I show some detailed UI. So the figure provides the depiction of the interactive segment process. The figure demonstrates the use of the two types of points, the positive clicks and negative clicks, just like what I talked about at the very beginning, how the point-based interactive segmentation works. The positive clicks are placed directly on the target land cover segment, indicating the desired area for inclusion within the segment. And conversely, the negative clicks are positioned on regions considered irrelevant or not belonging to the intended segment, serving as markers for exclusion. And here's another figure portrays the example end product derived from the interactive segmentation process. So here you again, this kind of the result can be exported in GeoJSON format. It can be imported again to your tool or exported to other GIS platforms. And the tool has two predefined classes, tree and building, but you can add any more classifications you want. Like in this figure, I added a car class, and you can see I can just also classify the car And also the tool assigns the distinct colors to the different object classes. Not like other some segmentation tools, they give all different colors to the all objects. So this, I know that currently in the market, there are many kind of the interaction segmentation tools as well, but most of the tools, they only designed for those really normal photos, like the pictures or photos you use your phone or your camera take every day. For this tool, we only designed for the remote sensing images. Like the very beginning, you can see we can optimize the value range because we know that the different satellite images have the different value range. And also we can select it the bounds you want. And since we know like the hyperspectral images, they have really many bounds, just many bounds that you want to use. So in this tool, you can select the bounds you want to input for this model. And I know that some of the geography researchers, they also developed some segmentation tools based on the SAM API for the remote sensing images, but I tried some of these. They lack of the interactability, and also like us, we really designed it for the classification to meet those remote sensing requirements. So in my today's talk, I talk about that deep learning has emerged as a significant tool in the field of remote sensing applications. Its capability in extracting essential features, particularly through segmentation and classification techniques, are indeed promising. However, within this broad scope, the application of deep learning for interactive segmentation and lab cover classification remains less explored. My study indicated to this under research area and focus on evaluating distinct interactive segmentation methods. I considered various factors in our assessment, such as net cover types, object sizes, and spectral combinations. And interestingly, in contrast to our initial expectations, it was the simple click models that stood above the rest in terms of the performance. And conversely, the popular SAM method illustrated less efficiency when applied to the remote sensing images. And in building upon these insightful findings, I went into the development of a new online tool named RSISEG. This innovative tool enables an interactive segmentation of remote sensing data. A unique feature of RSISEG is its integration of a high-performing interactive models, which distinguishes from existing tools in the market. Apart from this, RSISEG is designed to offer robust interactivity, modifiability, and adaptability, adding to its high efficiency and appeal. So that's all about my today's talk. I still miss a lot of interesting stuff in my paper due to the time limit. Like I also talk more about how the remote sensing data, the spectral properties plays in the deep learning model training, and also for the comparison between the SAM and those the simple click models. We have also some really deeper discussion. So if you're really interested in it, feel free to contact me. That's all for my today's talk. Thank you.
Yeah, thanks a lot to Jeff for this wonderful talk. We do have time for comments and questions. Anyone from the audience?
If nobody else has any, I do. This is Ruth.
Yeah, go ahead, Ruth.
So this is interesting. And I guess you mostly have been looking at cityscapes, but at the moment, some of the more interesting remote sensing problems are related to, for example, disasters, where in the case of floods and things, I think your cityscape work might be useful from a before and after standpoint. But during a disaster, like say a wildfire, where that might be more of a forested area, how likely, or have you done any work on seeing how well these kinds of classifiers would speed up that? You know, for example, in helping firefighters understand where hotspots are, where they're moving, you know, in other words, how quickly can these things analyze new data as they're coming in? Because I know that's a pretty big concern, particularly out here in the West.
Yeah, I have to say that I didn't have any experience in dealing with the welfare using remote sensing, but first, like what I show in my ESIP tool, like the demo, in my demo, the image is the image I have never used. So that means first we can try to just apply those remote sensing images, build a wildfire into to see how that works. And even though it didn't you won't perform that good, we can use some wildfire remote sensing images with the labels to train those model again. That will be really quick. That is not that difficult as imagined if we want. But just like say, I couldn't say how that perform is we directly put an image with the wildfire to my tool at this time. But that will be really easy to train the models with the welfare data and then be used to the further applications in those welfare prediction or welfare classification like that.
Cool. So you should know that there's a disasters cluster wildfire group that's thinking of, tools to make the issue of dealing with wildfires both before, during, and after more tractable. You might want to consider, attending some of their telecons to see if there's any mutual interest there.
Yeah, that is interesting. I can maybe after this meeting, I will try to find some data to try first to see whether my tool can just without training directly to detect the wildfire areas based on the remote sensing images. That may be the first time. If something interesting findings were found, and I can try to see whether my tool can be applied to the some wildfire detection, like those kind of the related applications.
Cool. You're on mute.
I was muted. Yeah. I do have a follow-up question. Because here is a semantic committee. So in semantic modeling, we do have this granularity level, basically like to describe an object at the different levels of details. Like the example you give to us, I think you gave an example about you can also segment vehicles. You call it a car, right?
Yeah.
But in your image, actually, I can see they are both like a house, like house-use mobiles and trucks. So is there a possibility to go to a finer scale so we can recognize what segment, not only treat them as a whole group car or vehicle, but also we can take out trucks, pickups, cars, also minivans?
Of course it can. That is just like what I described at the very beginning. The interactive segmentation try to solve the problem. If you don't have the predefined classes, you give in my tool, you can give any classes you want. Like I can just give this is the truck and this is the one, and you give the. But one more problem is like my current training data set, they only contain the class of cars. And I know there are some existing data set that contain the finer labels, so we can fine-tune our models with those data set first, and then it can better tell like the different types of the cars.
That's great. Do we have any other comments or questions? Okay, let's thank Dr. Wang again for this wonderful talk and
thank you.
The interactions with the audience. Megan, should I stop recording? Because we're moving on to the business stuff.
Yes, I think that's reasonable.
Yeah, okay.